Before getting on with the next lesson, I just thought I'd take this opportunity to mention a couple things first. As I was preparing this lesson, I noticed again another bug in my debug dump thing. And, well, what was happening was I wanted it to print out, let's say, 200 and something X bytes, and it would give, these dumps. If you dump and it's out of line, like now, I realize it seems like a silly aside, but I ended up wasting almost an entire day, or almost 2 days, working on this silly little problem for no reason. It would start printing here, and then it would get to its limit of 100, so here, I guess. And then there would be a carriage return, and then the next line would start here, and it wouldn't end up being nice and solid like that. And I went to the code, and I saw, okay, what's happening is every time I print out one of these blocks, I'm printing a carriage return and a line feed. And so I shouldn't do that, especially if there's more data coming. And so I thought, okay, well, this is probably not too hard to fix. It's just a carriage return. I go into the code and look at the code. Blah, okay. And I figured the problem was in here, where it prints a carriage return at some point. And I wanted it to not do that if there was more data coming. It's in this wob cars. Wob cars are these little things on the side, see? When you get to the end of the line, then you want to print out like a textual representation of the string. So the problem was with the wob cars. And okay, here it is. Here I'm printing out a carriage return and a line feed every time. And then I figured, okay, well, what I'll do is, I know that dx, so the point I'm trying to make here is that I violated some of my own advice and principles that I've always used and never veered from, and it hit me as it has before every time I've learned this lesson. And here's the lesson that's coming up now. Here is this function. Now it prints out a carriage return. It always prints out a carriage return. And that was the problem. Because when the data was coming in out of line, it was printing out a carriage return that I didn't want. Now, the function that calls this guy is this thing that writes out the block. And the function that calls that one maintains the amount of data remaining in this dx register. So down here I figured, okay, well, it's easy. All I'll do is, if dx is not 0, I won't print out a carriage return. Now, even if this did work, this not printing out a carriage return on the basis of the value of dx, at this point, anyway, if there was a death penalty available for computer programming mistakes, I would have deserved one at this point, because what I've done already is committed one of the worst coding violations you could possibly commit as a computer programmer. Is a professional programmer would never do such a thing, and neither would I. Normally, I knew I was making this mistake, and I thought I would be able to get away with it, but I didn't get away with it, and I did get bitten by it badly, and that violation is exactly what I just said. Here I am, a function being called by this function, which is being called by this function, and I'm using a little piece of data being maintained by the function that's calling my function, and using that as the basis to decide what to print out. That is, I'm taking advantage of a little implementation detail of the parent's function that I have no business thinking about, and using that to make a decision. Now that's fundamentally wrong. That's like using memcopy to copy overlapping memory blocks. It's undefined. There's no reason why this function has to use dx. I thought I would get away with it because I'm writing both functions. So if it works, then I'll be done with it forever. But it doesn't matter. Even if it did work, which, as I said, it didn't work for some fairly obvious reasons, I should not, and I hope never again, make that mistake. Never, ever, ever take advantage, or attempt to take advantage, or even think of attempting to take advantage of an implementation detail of another function. See, in the back of my mind, I was thinking, well, maybe the parent function, if this works, it could pass it in as a flag or something, don't print carriage return. That was in the back of my mind. I thought, okay, we'll try it. If it works, then I could fix it up later. But still, even if I fixed it up, there are a number of other reasons why this approach is wrong. Not the least of which is the fact that it doesn't work. Well, what does happen when I don't print out a carriage return on the basis of the fact that there's more data coming? On that basis, what happens on the next time through the loop should be easy enough to figure out, because every time into that function it does exactly what it always does, and the next time in it'll do exactly what it always does. So first I get 100 bytes to print out. That means I print an address, then I print a bunch of spaces, then I print 2 bytes at the end, and then I print these little wob cars, and then go on to print all the rest until it stops at some point, like here, say. It would be this case, it would be exactly like this. Not including. I know. E. Exactly like this scenario. That's 100 bytes from here to here, and now the cursor is sitting here. Okay? Now, the function gets entered. Without any other changes, it's going to start writing out the 14BF at this point here. This wouldn't be here yet, because this thing is a stream print. There's no scanning backwards and forwards. It has to wait till it gets to the end of the line before it can do this, the extra bit. So then the next time through, I haven't printed a carriage return. I do the usual, 14BF 100 goes here, and a bunch of spaces that wrap around, and then the 2 bytes. Okay, well, that's pretty bad. What I want to do is, if I come in here in a situation where it's not the first line. You see, we had a problem with the last line. Now we have to worry about, is it the first time? In that case, I don't want to print out the header part. You see how this small problem, which could have been easily solved, is suddenly starting to balloon into an extremely difficult problem. We've got to get back in here and somehow figure out, is it the first time we've been called? Were we waiting for data on the last iteration, and now suddenly we have to have memory. We have to remember what the state of the last was of the last time the function was called. And it becomes a very, very, very difficult problem. And after about, 10 hours of different methods and trying to figure out things one way or another, I finally got it down to something like this. And it's too bad for me that it almost worked. Because if it was a complete failure, I would have given up and gone on to the correct solution. 10E. See, in fact, the amount of data supplied was like this. Something like 2fx, say. Or maybe less, actually, or else I would have seen it earlier. I was unlucky in that, let's say, 20f? Yeah. See, I was unlucky in that if there had been one more line on this printout, I would have given up on the approach instead of continuing to pursue it. Because after figuring out a way to decide not to print this, the answer came out exactly like this, with only one tiny little problem, and that only the last two wob cars or whatever got printed out. You see? And so it looks like the problem was almost solved. And so all I had to do is just figure out how to get, this little bit of data. Because, as I said, it's a stream thing. The function stops here, goes away, comes back. Somehow I figured out not to do this bit. Then I do this bit. And now how am I going to do this bit when I don't know any more about the last line? So now I'm thinking, okay, I'm going to have to remember the last line and all the details about the last line. And it's becoming an impossible problem, right? In fact, I would say that it is an impossible problem in general, and that there's no need for such problems as this for the following, well, maybe not reason, but you see, the function as it was giving the wrong answer, I would say it was working perfectly. When it gave an answer like the case where it will come out like this, 2D, and then the next line would have the next two here, and so the next line would look like 0 D E 3 O. No, 3. I'm doing 100. 3 O D. Right? Yeah. That is correct. That was the answer that it gave the first time, and that's working perfectly. And there's no reason to change something that works perfectly. What we're doing instead of taking a thing that works perfectly and is working in a perfectly predictable and reliable way, and changing it to make it do something that it wasn't designed to do in the first place, and asking it to do something that is nearly impossible in the first place, is wrong. That means we're asking this thing to pretty much solve all the problems, like just make breakfast and so on. It's this here's where the problem is. It's this guy asking this thing to do the impossible. Okay? And that sort of forgives this one for taking advantage of that one. There's like a little war going on here. And actually, I would say that if this function, this DOS debug dump, cast a flag into this function indicating whether or not to print a carriage return because there's more data coming, then this function is bullying. I would say is bullying this one. It's asking it to do the impossible. It's asking it to do more than it should have, than it was designed to do. And that's why I've got this written in capital letters. Actually, originally I had this, once I realized what a fool I was being, I'd had this here in this part was in capitals, and all separated. Telling this guy up here, I'm doing enough already. It's your problem. You deal with it, because there's no way I can handle. I'm not going to become a state engine for your problem that you can't handle. How to pass data correctly to a function that gives a perfectly predictable, correct result every single time. And after I'd made that decision, it was a matter of minutes almost before the problem was solved. I mean, we're talking about 10, 12 hours of impossible search, because I thought at every point I thought it was almost fixed, to just a few minutes to think about the problem, try to figure out what's wrong, why it's giving, where the problem really lies, and what would be a decent fix for it. And I did find, and what came out of it actually was a very useful little utility. And I'll show you that right now. Just pause. Hang on. Okay, just save some time there. What I did was I started doing the problem inside. I started trying to solve the problem inside here, and there were too many labels and cases and so on, and I figured better to just separate the problem out and work on it in its own file and try and figure out the problem. Now, I'll show you the result first. This function was all I had to figure out how to write down. What does it do? It takes the remainder of something. That's it. That's the answer. Okay, now how does it work? Well, it does a little bit more than that. It's specifically designed as a kind of a number manager. Let's look at the test program. Basically, it feeds numbers to you in blocks. Okay, now I'm not giving a parameter. It would, if you were going to generalize this, you would give it two parameters: the maximum amount of number you can handle at any given time, and the alignment value you wish this second number to be aligned with, like on boundaries of 4, 10, 17, whatever. Okay, and this function's job is to tell you how much you should reduce this by in order to get it to line up in values, in chunks of the amount that you've told, up to your maximum value that you can take. Okay? And that's what that does. So it's easier to just step through it. Here in this example, I've taken 307, so that's how many total, sorry, no, it doesn't have to be bytes, it could be apples, it could be, Halloween parties, it doesn't have to represent anything. But I can eat 307 beans from a bag which wants to dispense beans on 10 hex boundaries. Okay? So I want this thing to come out as, if possible, on a boundary, a 10 integral value of 10 boundary from this, up to a maximum of 100 at each time, and then I can do whatever I want with that information. Okay, I might only call it once, but it's designed for calling over and over again. It's debug. I've already compiled it again. Alright. Okay, so here we are, starting it. I've just traced through the initial step. CX is a count of 307. SI is my source. It doesn't have to be a source, it could be anything. So now I'm going to call the function in the way that it's designed. If you push both values on, call the function. No need to step through the details. You just watch how it works. Function says that if I want to proceed in the way prescribed, I should subtract B from 415. Okay, so I'm going to do as it says. And I've done, sorry. Where's my subtract? Oh, I haven't done yet. I have to add, sorry. I should subtract B from myself, because I'm the one that's eating, and add that to this, because this is a moving forwards type thing. Now you'll notice that this has gone from an oddly aligned thing now to a multiple of 10. Okay, now check, see if I'm empty. I'm going to call the function again. And I've passed in my value and the same SI, whatever, after it's been modified. And now it says that I should take away 100, because that was our predefined maximum, from myself, and add that much to this. Now, you see what's happened here. I get 100 again. Alright. Moving around. Now, this should be the last time, because I don't have enough space for my full amount. So it'll give me, it should return FC, which it did. Subtract that from myself. That makes it 0. Done. Okay. Now if I take that highly predictable function that I'd already written and pass bytes into it in the order prescribed by this method, then I will get exactly the outcome I want. The first time it'll print out that address. Let's not go on. This is good for getting junk into memory. this was a case that I'd get something like this, worst case scenario. As prescribed, it would say you should take 2 first. I take 2, I pass 2 on. And then it's going to give me blocks of 100, 100, 100, 100. And if that happens to finish on an even boundary, no problem, it's done. If it doesn't, then this is going to stop, and my predictable function will do its predictable thing and print out the correct thing at the end. In both cases, it works. In every case, it knows it doesn't need to know anything about beginning or end or whatever. Sometimes, when it's the first time in, it'll be on the first line, right? And if I'm passing data in 100-byte chunks, it's always going to print the first byte. It's always going to print the address, which I always want. And at the end, it's always going to print the first address, and always going to fill this with spaces, and always going to print this out properly every single time. I'm just taking advantage of something with a well-defined interface. So the thing to learn, the lesson to learn: first, never do that mistake I made, and that's bad. B, if you're stuck on a problem, and it's the kind of problem that you know what's causing it, but you still don't know how, and you can't fix it, then stop what you're doing and try to think of another way. In fact, this whole exercise led me to completely rewrite the other thing, the pre-parsing part that you're going to see next time, because I was violating some of those rules there, and I stopped to think about what I was doing, and I was doing a few things wrong, and there was a better way. It was like this. It was like just write simple, small functions that do very well-defined operations. Don't let anything be overloaded. Don't beg too much of any given function to make your breakfast for you or whatever. And the result is quite good. It came out very nicely, and I think it actually completely solves the problem of that parse and any command line. And now there was something else I wanted to add. Let me think for a sec. There was something else I thought I'd mention quickly to do with that that number, that little number machine that I used to print out in uniform aligned blocks. Is a general thing. It's a general utility and has general usefulness. For instance, in the case of memcopy I'm thinking of specifically, it happens to be that certain architectures, certain computers will not allow you to read or write from an odd address. Like if you wanted to read this byte only, that would generate the same thing as a divide overflow. And in that case, a function like scasb, an instruction like scasb would be illegal. You can only read 2 bytes at a time on even addresses. Also for memory transfers, if memcopy itself, not only in that case, but in general, will not transfer single bytes at a time. Like our memcopy, the one I wrote using that move SB, is the least efficient one available. Well, of course, the implementation of that is unknown. It might not actually do it 1 byte at a time, but I think it does. It's probably honest. But you see, these machines. I was just looking at this, looking it up here. On every computer has something called an address bus, and what it is in order to access memory from a device, like either RAM or video RAM or something, there will be a collection of wires, and you can transfer data on those wires every so many clock cycles. You can get one width worth of data. So the amount of data you can get is maximized. The rate at which the transfer occurs is maximized when you're using as many of those wires per cycle as you can. So it would be best not to transfer one single byte at a time, but to do it in units of, let's say, 2 or 4, or usually a multiple of 2. And I was looking at this here. Usually or frequently require accessing an individual byte frequently requires reading or writing the full bus width, usually a word, at once. And so what happens is the other bits that are transferred in that transfer, which have no use, are given to the controlling device to decide what to do with. Maybe it might store that, and if it's expecting another read, it'll ignore the next read or something like that. And in some cases, like this example here, this Visa local bus is limited to aligned 32-bit transfers. You can only send 32 bits at once. So if you want to read 1 byte, you have to read 4. So you can multiply the speed of your reading by 4 by sending everything in keywords. So that's one thing, and a couple others coming up in a sec. The next thing is going to be all on that the parsing problem, which I think is solved, and it's going to be a little bit weird. So, and it might take a few, maybe not. It might take a few. If it doesn't take many lessons to get through it, you should spend some time thinking about what the whole point or the whole meaning of this next little bit is, because it's pretty important. And this has to do with this thing I call virtual data, or virtualized data. And this is something that people have used and known about for years and years. And C++ is all about virtual functions. So there's a kind of an analogy between this virtual data idea and the virtual function idea. We've seen virtual data type things with indirection as an example. A data indirection was the file things, the job file table and all that, are examples of virtualized data. That's not the only way that it's used. There's a direct link between the concept of abstract data and abstract code. And if you can understand the one idea, you can understand the other, and vice versa. And understanding that principle, the abstraction principle, is essentially the whole point of C++, and the point I'm trying to get to. So there is something important to be learned if you can see what I'm talking about. It might seem completely trivial, but there's a deeper message. So I thought I'd mention that. Anyway, I'm going to chop this up and get rid of a few bits, and then we'll go on to the lesson. So see you then.